Today's online, I will introduce you the directional derivatives, which this was not taught last year, but I think it's interesting and it's essential for Lyapunov theories. Okay, so it's kind of complementary materials. And then we'll discuss what is global, semi-global, and local stabilities, and Lasalle theory, which is similar to the invariant set theory. So we have covered this. This is a quadratic function. C1, C2 are the coefficients. So any type of this function can be considered as a Lyapunov function, which is positive definite. And the configuration is like this, which is 0 at 0. Okay, here are some questions. If Z is PD, which means that the only intersect with the origin is at 0 at 0, right? Where Z is 0 and x1, x2 are 0. If Z is some constant, then all the x1, x2 satisfy this condition is considered as a level set, right? So it's like you take a slice on this shape, they will give you like a circle, right? If C1, C2 are 1, 1. And this circle is the set which are the possible location of x1 and x2, right? Because those x1 and x2 are satisfying these conditions. But the greater the z values doesn't implies the greater the norms. These two have different meanings. This is in the z direction. This is in the horizontal, or you can consider Euclidean distance of the state to the origin, right? Usually, we only care about these terms. When we discuss the stabilities, stable, unstable, or asymptotically stable, the definition is all about the norm of x. We say stable. What's the meaning or the definition for stable? We say x1, x2. The phase portrait for a stable system is like you start from here, and it's not necessary for the trajectory converge to the origin, but it remains bounded, right? Remain bounded in some distance. If initial condition is satisfied, if your initial condition is around the equilibrium point, then the solution is also around the equilibrium point by some epsilon. Then it's defined as stable, right? So this radius is considered as epsilon. Okay, and this is smaller than delta. Okay, and the radius of this disk is epsilon. So it starts around or near the equilibrium point. The trajectory, the xt will remain in a certain distance. That's called stable, right? But for the asymptotically stable, it has to converge to the origin, right? So stable, if this is stable, the set of stable, then asymptotically stable is in the set of, if it's asymptotically stable, it must be defined as stable, but not vice versa, right? 对吧？反过来就不一定了嘛。Asymptotically stable 一定是 stable， 但 stable 不一定代表它会 asymptotically stable 嘛，因为它 converge 到 zero。When we define this stable, the definition for stable, we all discuss about the norm of your states, your norms of your states, not about the Lyapunov functions or the z functions, because it's virtual. But what we care is physically what's the state to the origin. But unfortunately, we don't know the trajectories. That's why we are not sure about this. But this is known, right? This z function can be determined, right? But you cannot say, oh, if this z is greater than this z, then their argument or the norm of the argument will be the same. Then we talk about how the z function changes with time, right? And it depends on your trajectory x1 and x2, depend on your dynamics. And that's the time when we can introduce the directional derivative. So what is directional derivative? Imagine that in this 2D plane, you consider is a phase portrait. And in this surface is like a Lyapunov function. It is in the like z direction. Okay, the higher the value, the greater the Lyapunov function. This is similar to this cone. So what is directional derivatives? This is nothing about Lyapunov function. It's just definition for directional derivatives. And this has been covered in your engineering mathematics. So what is directional derivatives? Here it says f is this Lyapunov function, or in the function in the z direction. So it defines as how does f changes as the input shift in the direction of vector v. So the direction of vector v is defined on this phase portrait. Okay, it's a 2D dimension. It defined as the dynamics of vector field. We're trying to see when it moves from here to here along the v direction, okay, which is kind of the dynamics, right? Your x dot, right? When it moves from here to here, what's the change of f value, which is from here to here? And obviously it's increasing from here, right? So this is called directional derivatives. If we consider z direction as v, okay, x1, x2. In this plane, x1, x2 is phase portrait, right? Given some dynamics, if x is here, you have some direction here called x dot. It's a column vector. It's a vector, right? In the 2D plane. So this is the dynamics at this location, at this state, right? And if you define some Lyapunov functions or some whatever functions, this function have given some x in the 2D plane, you can find a corresponding value v, right? v x1, x2. And when you move to here, it's another v x1 prime, x2 prime. Okay. So how do you define the change of v? So I would say, with respect to time, the change of v is v dot, right? Okay. So this only discuss the change of v with respect to time, but we have dynamics here. The role of this vector come into play, right? So, and it's the dynamics. So somehow you need to put dynamics into here, right? And that's the chain rule come into play. So you can put whatever variable you like in here, right? WA. And in this system, because we care about dynamics, so of course you need to put x here because this is dynamics. So, and you have to put x here. So this is dynamics. So basically, this is the concept of directional derivatives. Okay, this is derivative, right? And along this direction. Okay, this is derivative along this direction. Here, this is the direction. Okay, and this is the gradient. Gradient represents the slope at this point, and it's 2D, so it's a surface. It's a normal of this surface. This is determined, right? This depends on what your dynamics is. If you are controlling car, robots, it's defined, right? It's defined as this. It's defined. You can do nothing with it, but you can redefine this V. If you don't like this V, because it doesn't guarantee that V dot is negative, you can find another V. You can recreate another V. Okay, maybe like this shape. And maybe this V, this new V, give you these conditions. Okay, but in these two cases, the dynamics never doesn't change. The analogy of this Lyapunov function is like mountains. When you go hiking in the mountains, any location here, around here, this is the slope of the trail, right? And you can go any directions. And the direction is determined by your dynamics, right? And assume at this time I want to go this direction. And if you follow this direction, then you know that your altitude is declining. That means that eventually you will get to the sea level, right? Because of these mountains, the shape configuration of these mountains. The only location at 0 is the origin. Height is 0, the only location is the origin. And you know this system is asymptotically stable, right? Even though I don't know what's the motion pattern of some dynamics, but I know the height is always decreasing. Eventually I'll get to the sea level, which is the origin, right? The analogy is this. But if I use the same motion pattern, okay, for different mountains, I choose different variable functions. Maybe mountain 1 doesn't always guarantee this, and I choose a different mountain, and this condition always holds no matter where I am. Then it's a good variable function. But the dynamics is the same one, right? So it's a sufficient condition, not necessary. If you find one, that's fine. But if you did not find one, that doesn't mean this system is unstable. You can keep continue find a new one, a new V, okay? Here is the same, similar to what I just said. Given a dynamic system, right, you can plot the phase portrait, which represent the dynamics. And again, it could be unknown because you don't know the solution. It's nonlinear ODE. You don't know the trajectories, but you know that every point, what is the direction it's trying to go. It physically exists. What doesn't exist or what is virtual is this variable function, right? And in this case, the variable function is the kind of this shape. And this is the phase portrait, which is lie in this 2D plane, okay? And these 3 circles are the variable surface on this phase portrait, and the projection is these 3, okay? According to this dynamics, the trajectory's variable function is this. You can see in this case, V is always decreasing, right? When you get here, the V is 3, right? So this level set represents V is 3. When you follow this dynamics, the trajectory is here, and you know that after some time period, V is 2, right? In this circle, V is 2. So V always decreasing until you reach the origin, right? But for the same dynamics, I choose a different variable function, which is 4 here. What happened is, I know it's V is 2 here, right? And V decrease because it's inside this level set, right? So this is a level set. And the level set inside this, the value will be smaller than this one, okay? The smaller size the level set, the smaller the value of V. Okay, so when here is V2, right? And you go inside, and I know at this point, or this point, V is smaller than 2. But when it reaches to here, V is equal to 2, so V increase, right? So this is not a good variable function. And the previous one, this one is better than the next one. Because V dot is always negative, V is always decreasing. But it's the same dynamics. Yellow line never changes, right? It's identical in these 2 examples. So the problem is, how did you find V? Just try. But if it's a linear system, and as I say, you can use linear matrix inequalities. So next, semi-global and local stability. So global stability means for all initial conditions. It's all about initial conditions. And for semi-global, it's all initial conditions provided that another condition is the gain are selected appropriately. Appropriately means depends on the initial condition, okay? And local stability means for some initial conditions. So for example, for global stability, if you find a V and you find your V dot after you substitute your closed-loop dynamics, okay, you have this V dot, which means what? for any x, no matter what the x is, this v dot always is negative definitely, right? Because no matter where x is, v dot is negative, so it's always stable. Okay, so it's global stability. For the semi-global, the example is this one. Okay, k is the control gain, which is the parameter you can select. For example, k is minus in the control. This k is in the control. Okay, you can select whatever k you like. Okay. In this case, as long as the part inside the bracket is greater than 0, v dot is negative. To ensure this is positive, it depends on the initial condition of x. If x initial condition is 2, this is what? 4, right? 2 squared is 4. Then you have to select k greater than 4 to make sure this one is smaller than this. And the summation will be greater than 0. And v dot will be negative, definitely. Provided that the gain are selected properly means it depends on the initial condition. And for local means not this and not this. The stability only guaranteed if you start from some local region, not anywhere. So for example, the global case is if you start from some point x0, it might be stable or converge to the origin, okay? For semi-global, you need to choose a k greater than some value. If k is 1, then only any initial condition in this range will be stable. You can increase k to be 2 to enlarge the domain of attraction. Then you cover this initial condition. This domain covers this initial condition because you increase the control gain k. So this now included in the domain of attraction, so it can converge to the origin. So this domain can be controlled by the size of domain can be controlled by the control gain. Okay, so this is semi-global. For local, you cannot do anything. For local, it means that if your initial condition is in here, and it can the guarantee that the path of solution can converge to the origin. But if you are in here, it will diverge. So it's all depend on the initial condition, and you can tell from what v dot looks like. Now, let's give you an example how you can use stable function to prove the stability. Consider a pendulum case. Pendulum can move around this joint. This ball is connected by this rod. So this is the governing equation, and we negate the mass of this rod. So this is governing equation from dynamics. And use this governing equation, you can write down its dynamics, okay, in the state space form. So now your state is x1, x2. x1 is the angle. x2 is angular velocity of this angle. So question is this system stable? Stable or unstable or asymptotically stable? You can solve the solution probably, I don't know, but can you tell from the dynamics, prove that it's stable, unstable, or asymptotically stable? Pretty challenging, right? And what you can do is use the stable function, design as this. And is this stable function PD or PSD? Is it 0 at 0? Or is it 0 only at 0, right? Because if your x1 is equal to 2pi, 2pi is not at the origin. More than one equivalent point can make this v to be 0. So it's not a good choice for this to be a default function. But here, just for example, so here x1 is theta, x2 is theta dot. Yeah, right? Now you take the time derivative of v. X defined as x1 and x2. So you can imagine this will be a row vector, this will be a column vector. 对吧? So what's this? This is from dynamics. Okay. is a column vector, and this will be a row vector. What's this? So it's v x1, x2, right? So what's this? The derivative with respect to x1. This is x1. Okay. x1. So there will be g L sin theta. Correct me if I'm wrong. And this is x2. Do that. Or g L sin x1. Maybe I just change to x1. So let's see. Make the whole process simpler. x1. Okay. So this is known. So what is v dot? V dot will be 0. Okay. So this times x 1 dot, right? This times x2, which will be g L sin x1 times x2 minus 这个乘以这个乘以这个，也就是 x2。Right? So it's 0. What happens? It's moving, right? The dynamics is not 0. If you substitute, consider x1 is pi over 3. But you can conclude it's stable. Because v dot is 0, which implies v is constant. What is v is constant? Level set. The solution line in the level set. So it's stable. It doesn't go anywhere. It doesn't converge to 0, but it doesn't go anywhere. So it's stable. In this example, the best you can conclude is stable. Because you don't have any friction here. So the energy doesn't go anywhere. It's free motion. There's no friction. Okay? So it makes sense for v to be constant, or v dot to be 0. Right? It just oscillate forever. So in this case, with friction, so here is the previous one is without friction. Now we add some friction here. The friction is inverse proportional to the velocity. So after you added this term and you evaluate v dot give you this. So now is v dot nd or nsd? Okay, nsd. Why? If you look at here, it's x1, x2, right? V is the function of x1 and x2, right? But here, v dot is function of what? x2. Where did x1 go? x1 can be any value which doesn't change v dot. So that means x1 could be 0, could be non-zero. If x2 is 0, v dot is 0. But x1 could be 0 or non-zero. It doesn't care. We don't care, right? It doesn't change v dot. That means not only the origin can make this one to be negative, definitely. The best you can conclude is stable because x1 is not constrained. x1, no matter what x1 is, this one v dot will be negative till x2 is 0. So v will not converge to 0, v. As long as x2 is 0, v will be a constant, which is not 0 because x1 might not be 0. So what does the v looks like? V, this is v. If x2 is 0, v dot will be 0. V is constant. Right? And not necessarily 0. Because x1 might not be 0, right? Because if x1 is not 0, This might confuse you. So if you think V2 is 0, this is 0. If X2 is 0, it only means V is a constant, which is not necessarily 0. Okay. 因为 V 大是0嘛 ，V 不变的嘛 ，V 不变不是 constant 吗？一也是 constant， 二也是 constant 啊，0也是 constant 啊，对不对？那它不会是0 ，Why is not 0? Why V is not 0? Constant, why is not 0? Because x1 is not 0. And x1 is a function of V, right? x1 is a function of V. If x1 is not 0, this will not be 0. Okay? So don't confuse that if beta is 0, V is 0. No, not really. That's because the selection of V at the bottom here. So this is x2, this is x1, right? When x2 is 0, which is where? At the bottom, right? They are 3 bottoms. But the x1 value are different, which is maybe 0 and maybe minus 2 pi m. So there are 3 equivalent points, okay? And this is not PD. This, as I mentioned, it's not PD, it's PSD, right? Therefore, you have multiple minimas. So the selection of V is very important. Otherwise, you need to solve a problem that you created. Can you imagine this? If beta is 0, which means the slope of V is 0, right? Which could be at different locations. And at these different locations, V is not 0 because X is not 0. So for example, if X2 is 0, which means it's at this line, right? This line, X2 is in the direction of this, right? So X2 0 is this point. So X2 0 and X1 could be any value, which is here. So anywhere on this line, V is a constant. V is constant, but X1 can be anywhere. And if you are at here, the V value is greater than the V value here. The conclusion is there are many theories to tackle each of these situations. For example, a beta is negative definite, beta is semi-definite. What will happen? And there are many different cases. Okay, and there are many theories to use to prove that stability. Like next time, invariant set will be 1. Okay, and Lasalle theory is to prove that this kind of dilemma.